Welcome. Today we're going to talk about area between curves. So first we're going to do the idea of the area and come up with a formula for it, and then do some examples. So here's the idea. We want this area. So I'll even shade it. I'll shade it in blue here. We want the area between the function f of x here and the function g of x. Hopefully you can see the first task might be to find what these two endpoints are. It might be given in your problem, but if it's not, we've got to figure out what those are. But the second task is to figure out how do we even write that area. So the trick here is to notice that that area there, the blue, is part of everything that is right below f. If I finish drawing to the bottom here, the red plus the blue is the area under f, the integral of f from x equals a to x equals b. And actually the red part is the same thing for the g of x function. So if we just find the whole thing, the blue plus the red is the integral of the first one, the red is the integral of the second one, and we just take the difference, then we're good. So what is this area between the curves going to be? It's going to be the integral from a to b of the f of x, which tells us all of it, minus the g of x, which is just the bit below. And that's what we want. Now, that's a good way to write it, but f and g are abstract functions. What's probably a better way to write this is, in fact, to write it as the integral from a to b, or start to stop, of the top one minus the bottom one. It's important to remember, the area between two curves is not signed area between two curves. It's actually area, so it's always positive. So you want to have bigger minus smaller, pretty much always. Now, let's think about that. Notice over here, g is the top, but in the part we want, g is the bottom. Now, it may become more complicated. In some cases, one may be the top at certain parts, and the bottom at other parts, and you know what? Let's worry about it when we get to it. So, how do we figure this out? Let's take an example. The area between y equals x to the fourth. The first thing to do is to draw a picture of this. Y equals x is easy to draw. It's a straight line. Y equals x to the fourth is also easy to draw. It looks kind of like a very steep parabola. And you can see, hopefully, that this part that I'm shading in is what we want. And you could probably also see that it seems reasonable. Right there and right there are the intersection points. And this keeps getting bigger. There's not going to be any more over here. That keeps getting too big compared to that one. Those are the only two intersection points. How do you find them? Well, you can sort of tell from the functions what they are. But let's do it more formally. I want to know where this function and this function intersect. Where that value and that value for the y's are the same. So if we want intersection, we set them equal. So I need x equals x to the fourth. Or rather, x to the fourth minus x is 0. I just brought everything to one side. How do I do that? Well, at this point, I'm going to factor. I can factor an x out of that. And then I've got two things that are potentially 0. If something times something is 0, that means the first one is 0 or the second one is 0. 0 is special that way, so that's the only way we can do it. Now this first one, x equals 0, that's right there. This one, x cubed minus 1 is 0. For odd powers on the real axis, there's only going to be one kind of solution here. And then this case is x equals 1. So hopefully you can tell. 0, those are the same. 1, plug it in, they're the same. So we're going to have an area. The area is going to equal the integral from 0 to 1 of the top one. From the graph, you can tell x is the top one. Just look, it's higher up in that region. So it's going to be top minus the bottom dx. That's our area. Now we can anti-differentiate, get the answer. The antiderivative of this plug in the endpoints. I get 1/2 minus 1/5, then minus 0 minus 0, or just the 1/2 minus 1/5, which is in fact 3/10. Try this one out. I'll give you a couple seconds. You can pause, see if you want it. It's got a trick to it. It's not quite as easy, but hopefully you'll see it. Maybe you did, and if not, or even if you did, let's work through it. x to the fifth kind of looks like a flatter x to the third, well, flatter and steeper. And x to the ninth is even more so. And I've done this carefully. There's two curves there's two pieces in here. It looks like they bump into each other in the middle. So let's figure out the first step. The first step is to figure out where they intersect. We say x to the fifth equals x to the ninth, which means x to the ninth minus x to the fifth is 0. Factor out. How do you factor this? Let's see. Well, x to the fifth comes out, x to the fourth minus 1. So either x to the fifth is 0, which tells us that x can be 0, or x to the fourth minus 1 is 0. That, because x to the fourth is even, can factor into two pieces, x squared minus 1 and x squared plus 1. X squared plus 1 can't be 0, but x squared minus 1, because the 2 is even, that can be x minus 1 and x plus 1, which gives us x equals 1 or minus 1. Let me rewrite all of these three. We have three intersection points, 1, 0, and minus 1. What do you do with three of them? When I had two of them, I just put the lower and the top, the earliest one and the end one. But I've got three, so how do I do that? There's not three spots for numbers on an integral. But what we can do is we can make two integrals. For the lower part, we can say the area then, is the integral from minus 1 to 0 of something, dx, plus integral 0 to 1 of something, dx. And we just have to figure out what goes in there. So what does go in there? Top minus bottom. So between maybe it's the same in each case, but it could be different. So from minus 1 to 0, over here, which is the top one? Well, I'm not so sure. So I'm going to try it. I'm going to try out. Say what's something between 0 and what's between that? Try that again. Between minus 1 and 0, what's something in there? It's going to be like, how about minus a half? Put a minus a half in here, you get minus 1/32. Put it in here, you get minus 1/512. That's smaller. But with the minus sign, it actually is higher up. It's closer to the axis. This is the one on top, in the negative place, not that one. So we want the top minus the bottom. And for the same kind of reasons, over here, the x to the ninth is closer to the x-axis. It's the bottom one on that side. So x to the fifth minus x to the ninth. Notice, if you forgot that and just used one minus the other throughout the whole way, it'll end up canceling out, and it shouldn't, because there's actually area in there. Some area here, some area there. So let's try this out. Anti-differentiate. We have 1/10 x to the 10th minus 1/6 x to the 6th. And over here we have 1/6 x to the 6th minus 1/10 x to the 10th. It's worth noting that regardless of the direction you do, you're going to get the same kind of answer. It's not like we have two completely separate integrals. We have two integrals, it's true. But the anti-differentiation in each case is the same thing plus or minus. So put a 0 in here, we get a 0 minus 0. Subtract off, put minus 1 in, we get 1/10, and to the 10th power makes that even, minus 1/6, and again, even, plus, put 1 in there, 1/6 minus 1/10, subtract off 0 minus 0, and I get minus a 10th, plus a 6th, plus a 6th, minus a 10th, so 2/6 minus 2/10, or 1/3 minus a 5th, which is going to be 2/15. One more to do here. This one's tricky looking. The area between y equals x squared and x equals y squared, this is an implicit function. So that's going to make you go, ooh, I don't know what to do. But it's not hard. It's just the same thing. Draw the pictures. Y equals x squared. What does that look like? Looks like this. X equals y squared. It's the same kind of thing, but the x and y axes are doing the opposite thing. It's this. Yeah, badly at drawing it. But notice, there's only one part of intersection, and it's right in here. Now, there is the trick. What do you do to set these equal? Well, y equals this. That's not y equals. But in this case, this is y squared equals x, or x equals y squared. We could solve that. Y would equal plus or minus square root of x. And we could try plugging in each, but we know the minus part's not important. Let's try only the plus one, because the plus one's the only one where there's an intersection right up here. So y equals plus square root of x versus x squared. Solve that. Hopefully you can see now, that's messy, but what would you do? I'd square both sides, because that makes it a little easier to work with. X equals x to the fourth. And actually, you know what? To save some time, we notice we already wanted the spots between x and x to the fourth. 0 and 1. So we want the area between 0 and 1, of the top minus bottom. And in fact, if this is y equals square root of x, right here, and this is y equals x to the fourth, we just want the top one minus the bottom one. This one was written in a scary fashion because it's an implicit function. But it's not scary. It works just as well as any others. Except this is now what? X to the 1/2 power. So if that's x to the 1/2, we add 1 to that, so that's 3/2. So it makes it a little bit trickier. That's 2/3, by the way, because it's 1 over a fraction is the reciprocal. So we're going to have 2/3 plugging in with a 1, so 2/3 minus 1/5 minus plug 0 in. 2/3 minus 1/5 is going to be how many 15ths? 10 minus 3 is 7 15ths. And there you have it. Hopefully, between these examples and the theory, you see it's not super hard. You just need to find the endpoints, figure out which one's on top, plug in the integrals, anti-differentiate, and then solve. And then add and subtract and stuff. Until next time, this is Dr. Jet.